If you look at a product on a factory floor, whether it's, a massive structural steel beam for a skyscraper or just a tiny microchip for a smartphone, for about 80% of its life, it is doing absolutely nothing.
Nothing at all. It's wild.
Right. It is just sitting there.
Yeah.
So welcome to today's deep dive. Today, we are looking at the mechanics of time management and specifically planning detailed schedules to figure out why that happens. And, more importantly, how to manage the actual math of waiting.
Yeah, the math of waiting is a great way to put it.
We're taking this massive stack of sources on manufacturing execution, so operational playbooks, routing data, capacity loading models, and production activity control methods, and we're extracting the underlying logic of how these incredibly complex projects actually survive contact with reality.
It's a really counterintuitive reality to confront, too. Because when we think of manufacturing, the mental image is always motion.
Right, sparks flying.
Yeah. Exactly. Machine stamping, assembly lines humming, people moving. But as our sources reveal, the true battleground of throughput isn't the motion. It's the dead space in between all that motion.
Right. And to manage that dead space, we first have to agree on how we even measure the anatomy of lead time, right? Because for anyone who has ever tried to optimize a workflow, evaluating throughput forces you to brutally separate value-added time from non-value-added time.
Yes. The stuff that actually matters versus the stuff that's just waste.
Yeah, so, okay, let's unpack this. You have the runtime, which is the actual physical transformation of the material. That's your value-added time.
Right, the metal being bent, the chip being soldered.
Exactly. Then you have setup time, prepping the machine. But the massive bucket that actually shocked me in these sources is the interoperation time. So the cue, the wait, and the move.
Which is where that 80% figure you mentioned comes from.
Oh, wow, really? That entire chunk?
Yeah. Queue time, which is just waiting for an operation to begin, is almost always the largest single component of total lead time.
That is crazy.
It is. And when you evaluate true throughput, you start to realize that managers who obsess over shaving, milliseconds off their runtime are often fighting the wrong war.
Right.
What's fascinating here is that the system constraint isn't how fast the machine stamps the metal. It's how long the metal waits to be stamped.
I was actually trying to visualize the scale of this, and I kept thinking about going to a massive theme park.
Okay, yeah.
So you pay your ticket, and the value-added time, the runtime, is the 2-minute roller coaster ride.
The fun part.
Right, the fun part. But the queue time is the 2 hours you spend standing in that miserable zigzag line.
Yeah.
So if the park manager wants to increase the throughput of guests experiencing the ride, making the roller coaster run, 5 miles an hour faster, barely moves the needle. They have to attack the line itself.
That's a solid baseline. The theme park analogy works, but on a factory floor, it is actually significantly worse.
How so?
Well, unlike guests who are, standing neatly in a queue, parts in a factory queue physically block other operations.
Oh, right, because they take up actual space.
Exactly. They tie up massive amounts of working capital, they risk obsolescence, or they could just get damaged sitting on the floor. If a theme park guest waits 2 hours, they're just annoyed. Right?
Yeah, they complain on Yelp.
Right. But if a batch of aerospace components sits in a queue for 2 weeks, it is actively suffocating the factory's cash flow and its floor space.
So if 80% of our time is just products sitting in a queue, suffocating the floor space, someone has to be actively managing that dead space.
Yes.
But the master planners in the boardroom, the people generating the master production schedule or running those big MRP systems, they aren't down in the noise to do it.
No, they're looking at spreadsheets.
Right. So that massive gap between the pristine spreadsheet and the messy, chaotic reality, that's filled by production activity control, or PAC.
Yeah, PAC. PAC is the execution arm. If MRP is the strategic plan, the grand vision, PAC is the tactical deployment.
Boots on the ground.
Exactly. It is the real-time feedback loop. It tracks work in process inventory. It provides early warning signals when work centers are overloaded, and it actively attempts to shorten those queue and move times we just discussed.
But to actually function, PIC has to ingest and reconcile an astonishing amount of dynamic data, right?
Oh, absolutely.
Which is where the friction really starts, I'd imagine.
Yeah.
Because PAC is pulling in bills of material, the BOMs, to know what parts are required, but it also heavily relies on routing files to dictate the exact sequence of work centers.
Yeah, step A to step B to step C.
So what happens on the floor when the BOM says one thing, but, a sudden shift in available materials means the routing file requires a completely different path?
Well, that is exactly the type of chaos PEC is designed to absorb.
Oh, cool.
Theoretical planning assumes infinite stability, right? That everything will go perfectly.
Yeah,
PEC operates under the assumption of constant failure.
that's a stressful job.
Very. If a primary work center goes down, a machine just breaks, PAC has to reference the item master files and alternate routing data to instantly reroute that work in process without violating the BM constraints.
Wow.
It's basically an air traffic controller, constantly dealing with changing weather, low fuel levels, making sure the orders authorized by upper management actually have a physical path to completion.
Okay, so having that map and those ingredients, that's just the prerequisite. The real execution challenge is how PAC places those tasks on a calendar.
Yes, the scheduling.
Right. Our sources outline two main philosophies for this, and reading through them, it really feels like a massive timeline tug-of-war between forward scheduling and backward scheduling.
It is a tug of war.
Forward scheduling seems highly intuitive to me, though. Like,
Yeah.
you start the moment an order is received. The logic is just, if I begin right now, when is the earliest I can ship it?
It is intuitive, and it's highly effective if your primary goal is high machine utilization,
Yeah.
keeping machines busy, or leveling out the load on your resources over time. But the direct consequence of forward scheduling is that it builds up massive inventory.
Ah, because you finish early.
Exactly.
Yeah.
Because you are completing operations as early as possible, the finished goods often just sit in the warehouse waiting for the actual contracted due date.
So you basically trade one queue for another. I mean, you clear the factory floor queue, but you create a warehouse queue of finished goods.
Exactly. Which is why many systems, particularly those driven heavily by lean principles or, strict MRP logic, they default to backward schedule.
Right. Working backward.
Yeah, you work backward from the due date. The logic there is, when is the absolute latest this must be started in order to finish precisely by the promised date?
And the result is less inventory.
Significantly less inventory buildup because the product rolls off the line right when it needs to ship.
Okay, look, I have to push back on that because in a post-supply chain crisis world, isn't zero buffer backward scheduling incredibly dangerous?
It's definitely stressful.
I mean, if you plan to start a massive complex order at the exact last possible second to hit a deadline, you are leaving zero margin for error. If one machine breaks down or one delivery of raw materials is just a day late, you're instantly late on your delivery. It sounds like walking a tightrope without a net.
It does, and it's a very valid concern. But you're viewing buffer as a safety net, whereas from the perspective of manufacturing finance, buffer is a massive liability.
How so?
You're absolutely right that backward scheduling introduces severe operational risk. However, holding inventory is incredibly expensive.
Oh, right. The warehouse costs.
Yes. Finished goods sitting in a warehouse, they tie up capital that can be used for R&D, they take up physical space that requires heating and lighting and security, and they risk damage or becoming obsolete.
So it's a calculated gamble. You accept the operational risk to achieve the financial reward of lean inventory.
I'd say it's less a gamble and more a forcing function for extreme discipline.
Oh, I like that. A forcing function.
Yeah. Because backward scheduling relies on highly reliable work centers and precise execution. You simply cannot run a backward scheduled floor if your machines constantly break down.
Right. The whole thing falls apart.
Exactly. Therefore, it forces the organization to invest heavily in preventative maintenance and rigorous quality control. The lack of a buffer exposes the hidden inefficiencies in the system, and it forces you to fix them rather than just, hiding them under a mountain of safety stock.
Okay, that makes sense. It forces accountability. But that brings us to the next massive hurdle from the sources. We've mapped out our calendar using this highly disciplined backward schedule, but what happens when the calendar itself is fundamentally broken?
Oh, the capacity problem.
Yeah. Say the math dictates we need to run a specific routing on machine A for 80 hours this week, but there are only 40 hours in the shift. This brings us to the transition from infinite loading to finite loading.
And this transition is where theoretical plans usually hit a brick wall. Very hard. Infinite loading is a planning profile that shows the required capacity exactly when it is needed, completely ignoring whether the factory actually possesses that capacity.
It just pretends you can do anything.
Right. It shows raw, unadulterated demand.
Looking at an infinite load profile is wild. Here's where it gets really interesting. It's like a popular restaurant deciding to accept every single dinner reservation that comes in for 7:00 p.m. on a Friday.
Oh, that's a great way to picture it.
Right. The computer says, great, we need to seat 500 people at 7 p.m. It's an infinite load, but obviously the restaurant only has 50 tables.
The restaurant analogy is perfect, but the real-world friction of infinite loading on a factory floor is heavily political.
Oh, really? Between who?
Mostly sales and operations.
Yeah.
Infinite loading is often what the sales department promised the customer. They want to say yes to everything. Finite loading acts as the operational reality check.
Buzzkill.
Exactly. It caps the load at the actual capacity limit. If you have 60 hours of machine capacity this week, you only schedule 60 hours.
Right. You just count the chairs and tell people they have to eat at 8:30 p.m.
Yes. The rest of the demand must be shifted to another week, moved to an alternate machine, or you have to bite the bullet and authorize overtime. Finite loading is operations telling sales, I'm sorry, but this order is going to be delayed.
Which forces a massive operational bottleneck if not handled correctly.
Yes, and this ties directly into the theory of constraints. A system is only as fast as its slowest point, the bottleneck.
Right.
If you infinitely load a bottleneck work center, you are actually producing more goods. You are simply growing the queue time ahead of that center infinitely.
You're just making the line longer.
Exactly. Finite loading forces the organization to respect the constraint and pace the rhythm of the entire factory to match what that bottleneck can actually handle.
Okay, so finite loading solves the macro problem. It caps our hours, but that still leaves the micro problem on the actual floor.
The day-to-day.
Right. Let's zoom in. You have an operator standing at their work center. 5 different jobs are sitting in the queue in front of them, physically taking up space.
Yep.
The dispatch list says they all need to be worked on this week. Finite loading says we have the hours to do them all eventually. But who goes first right now?
And this is the granular reality of operations, sequencing, and dispatching. How do we direct traffic hour by hour?
Honestly, if I am that floor manager, I am probably just looking at the earliest job due date. Like, whichever job has to ship to the customer as soonest gets priority.
That's a common instinct.
Or if I want to clear floor space quickly, I might use shortest process time and just knock out the fast jobs first.
Both of those are standard dispatching rules, sure. But in a highly dynamic environment, relying on them creates a severe domino effect.
Really?
Yeah. Let's look at your first instinct. Earliest job due date. What if the job due on Thursday takes 40 hours of runtime, but the job due on Friday only takes 2 hours?
Oh, I see where this is going.
If you strictly prioritize the Thursday job, the Friday job, which is incredibly quick, just sits in the queue for 40 hours and ends up being late anyway.
Wow, okay. And if I do the opposite and use shortest process time, I knock out all the 2-hour jobs, but that massive 40-hour project keeps getting shoved to the back of the line until it is catastrophically overdue.
Exactly. Simple heuristics fail when lead times and due dates are constantly shifting around. That is why managers rely on more sophisticated mathematical formulas to truly rank urgency, specifically slack time and the critical ratio.
Let's dive into the mechanics of those, because this is where the sources get really fascinating. Slack time is a measure of the buffer you have left right.
Right.
So the formula is the due date minus the present date, which gives you the actual calendar time remaining, and then you subtract the total lead time remaining that's required to physically finish the job. If the number is positive, you have slack.
Correct. But slack time only gives you an absolute number. It doesn't give you relative urgency across different jobs.
Yeah.
That is where the critical ratio, or CR, becomes the ultimate index metric on the floor. It takes those same variables, but creates a ratio that instantly scales the priority of every job against each other.
The formula for critical ratio is the actual time remaining divided by the lead time remaining. And the sources provide this brilliant specific example to walk through. Order C. Let's apply this logic to Order C.
Okay, let's do it.
So the due date for Order C is day 56 of our manufacturing calendar, and today is day 48.
So step 1, calculate the actual time remaining. 56 minus 48 is 8. We have exactly 8 calendar days left until this product must be shipped.
Right, 8 days left. But the PACE system looks at the routing file and calculates that the total lead time remaining, so factoring in all the queues, setup, run, and move time required for the remaining operations, is 16 days.
Now we apply the critical ratio formula.
We
Actual
made it.
time remaining, which is 8, divided by lead time remaining, which is 16.
8 divided by 16 is 0.5, so the CR is 0.5. But knowing the math is one thing. Understanding the mechanism is another. What does a 0.5 actually trigger in the system? Like, what does that actually mean for the guy on the factory floor?
It triggers immediate intervention. Let's decode the scale. A CR score of exactly 1.0 means your actual time remaining perfectly matches your lead time remaining. You are precisely on schedule.
Perfect balance.
Right. A score greater than 1 means you have more calendar time than the work requires. You have a cushion.
So if a job is ahead of schedule, the CR is automatically pushing it down the dispatch list to make room for others.
Yes. A score of 0 or negatives means the due date has already passed, but order C sits at 0.5.
Right.
Any critical ratio less than 1 means you're bleeding time. You have less calendar time remaining than the work requires. You are actively falling behind schedule.
Because we only have 8 days on the calendar, but the system says the work takes 16 days. I mean, we are mathematically guaranteed to be late.
Which is why order C is a 5-alarm fire. When a dispatcher sees a CR of 0.5 on their list, that job instantly jumps to the very front of the line at every single work center it visits.
It gets the VIP pass.
Exactly. The critical ratio isn't just a metric, it's an automated override system that prevents the domino effect we discussed earlier. It balances both the calendar due date and the volume of work remaining to force the system to pay attention to the most mathematically endangered orders.
But wait, the Pegasus system, acting as our traffic cop, has flagged Order C. The sirens are blaring, but simply moving it to the front of the line doesn't magically bend the laws of physics.
No, it doesn't.
We still have 16 days of work and only 8 days to do it. How does PEG actually recover a schedule that is that deeply underwater?
By utilizing specific lead time management tactics to actively attack the non-value added time we started this entire conversation with.
Oh, full circle.
Exactly. When you are staring down a CR of 0.5, Pegasus has to physically shrink the lead time. And the sources detail 2 primary methods for this: lot splitting and overlapping.
Lot splitting seems like an emergency brute force tactic. Like you take a large batch of items, say 1,000 metal brackets, and physically split that lot in half. You then route those 2 smaller batches of 500 to 2 separate, identical machines to run simultaneously.
It is brute force, and it comes with a severe penalty. You incur the cost of setting up a second machine, which goes against every standard efficiency rule regarding setup times.
You double your setup time.
Yes, you are actively choosing to lose efficiency on the floor in order to buy back calendar days and save the due date. You cut the total runtime for that operation in half, but at a much higher operational cost.
You pay for the time with setup costs. Okay. Then there is overlapping, which attacks a different part of the lead time entirely. Normally, a batch moves serially, right? The entire batch of 1,000 brackets sits at operation 10 until every single unit is finished, and only then does the entire massive batch move to operation 20.
Which creates massive wait times at operation 10 and massive queue times at operation 20 while it just waits for the previous batch to clear.
Right. But with overlapping, you break that serial constraint. As soon as the first 100 brackets are finished at Operation 10, you immediately move that sub-batch over to Operation 20 and start running them, while Operation 10 continues chewing through the rest of the original lot.
Exactly.
So both operations are running concurrently on different portions of the same batch.
And this is where the entire system connects back to the core insight of these sources. If we connect this to the bigger picture, overlapping doesn't make the machines run any faster. It specifically targets the interoperation times.
The wait and the move and the queue.
Right. By overlapping, you are aggressively eliminating the wait time at the first machine and the queue time at the second machine.
You are systematically deleting the dead space.
Precisely. You are shrinking the 80% of the time the product is doing nothing. That is how Pawn T saves the due date for an order with a critical ratio of 0.5. It doesn't speed up the value-added work. It aggressively removes the non-value-added waiting from the schedule.
It is incredible how elegant the execution becomes when you trace the logic all the way through.
It really is an elegant system when it works.
We started by separating value-added runtime from non-value-added queue time. We saw how PEC acts as the execution arm, constantly adjusting the routing and the BIM-BOM against the chaotic reality of the floor.
Yeah.
We explored the high-stakes discipline of backwards scheduling to minimize inventory, and how finite loading acts as the ultimate reality check against infinite sales promises.
And finally, how granular dispatching tools, like the critical ratio, give managers the mathematical leverage to identify failing orders, allowing them to deploy overlapping and lot splitting to physically buy back time.
Right.
It is a continuous, relentless feedback loop.
So as you, the listener, process all of these operational playbooks, what does this actually mean for you? Because you might not be managing a chemical plant or sequencing a CNC machine this week. But since we established that queue time is often the single biggest component of lead time, I want you to critically analyze your own workflow.
The translation to knowledge work is almost entirely direct.
Completely direct. Where is your work just sitting in a queue, suffocating your throughput? Are you waiting for an email reply to proceed? Are you holding on to a massive document because you want to finish the whole batch before you send it for approval?
That's a trap so many people fall into.
Right. How much of your own personal lead time could you buy back if you started overlapping your tasks? Sending pieces of a project forward as they are done instead of waiting for perfect, massive batches to finish.
It is a profound shift in perspective. Once you learn to spot non-value-added queue time, you realize that most of the delays in your projects aren't because the work is hard. The delays exist because the work is just sitting there, waiting to be allowed to move forward.
Exactly. And it brings us right back to the core logic of these sources. Massive, complex projects don't avoid chaos by rushing the actual work. They survive by fiercely and mathematically managing the waiting.
True efficiency isn't about speed, it is about synchronization.
A perfect operational reality check for all of us to apply this week. Thanks for joining us out on the floor for this deep dive, and we will catch you on the next one.